Many aspiring software engineers spend years buried in textbooks, learning about distributed systems, data structures, and scalability patterns. While these concepts are important, there's often a disconnect between theory and the real-world systems powering the apps and platforms we use every day. The real turning point for many developers comes when they shift their focus from academic theory to understanding how actual products work. This video will guide you through 18 real systems that explain the majority of what you'll encounter in production environments, helping you bridge the gap between theory and practice. The realization comes when they can recite the CAP theorem, but can't explain how Netflix streams video to millions. The key is to stop treating system design as an abstract exercise and start reverse engineering the real products you use daily. When you do this, concepts like sharding, caching, and load balancing suddenly become practical solutions to real problems, not just theoretical constructs. This approach transforms your understanding and makes you a better engineer. If you're serious about growing as a software engineer, it's crucial to study real systems, not just theory. Real-world case studies reveal the practical challenges and solutions that companies have already implemented. By analyzing these systems, you'll gain insights that textbooks simply can't provide. This video will walk you through 18 case studies that cover 90% of what you'll face in production environments, giving you a practical foundation for your career. Every journey into system design starts with core infrastructure. These foundational systems are the building blocks of modern software engineering. By understanding how these components work, you'll be better equipped to design, build, and maintain robust applications. Let's begin with the first essential system, the URL shortener. URL shortener, like Bitly, is often the first system design interview question for a reason. It teaches you about hash functions, collision handling, and database indexing. You'll learn why base62 encoding produces shorter, cleaner URLs compared to hexadecimal, and discover that a simple key-value store is often enough for the job. This system is a perfect introduction to the practical side of software engineering. Hash functions are at the heart of many systems, including URL shorteners. They transform input data into a fixed-size string of characters, which is typically used as a unique identifier. Understanding how hash functions work and how to handle collisions when two inputs produce the same hash is essential for building reliable systems. Efficient database indexing is crucial for performance in systems like URL shorteners. Indexes allow quick lookups and ensure that retrieving the original URL from a short code is fast and reliable. By studying how real systems implement indexing, you'll understand the trade-offs between speed, storage, and complexity. base62 encoding is commonly used in URL shorteners to produce compact, human-friendly URLs. Unlike hexadecimal, which uses only numbers and a few letters, base62 uses both uppercase and lowercase letters, plus numbers, resulting in shorter codes. This small detail can have a big impact on usability and system efficiency. Many real-world systems rely on simple key-value stores for fast data retrieval. In a URL shortener, the short code is the key, and the original URL is the value. This design is straightforward but powerful, allowing for quick lookups and easy scaling as the system grows. When two different URLs produce the same hash, you have a collision. Real systems must handle these gracefully, often by checking for existing keys and generating a new hash if necessary. Understanding collision handling is key to building robust systems that won't lose or overwrite data. As usage grows, URL shorteners must scale to handle millions of requests. This involves distributing data across multiple servers, implementing caching, and ensuring high availability. Studying how real companies solve these problems will give you practical insights into system scalability. Caching is a fundamental technique for improving performance in large-scale systems. By storing frequently accessed data in memory, systems can serve requests faster and reduce the load on databases. Real-world systems use various caching strategies to balance speed and consistency. Load balancing ensures that no single server becomes a bottleneck. By distributing incoming requests across multiple servers, systems can handle more traffic and remain responsive. Real-world load balancers use sophisticated algorithms to optimize resource usage and minimize downtime. In distributed systems, achieving perfect consistency is often impossible. Instead, many systems settle for eventual consistency, where all nodes will agree on the data given enough time. This trade-off allows for higher availability and better performance, especially at scale. The CAP theorem states that a distributed system can only guarantee 2 out of 3: consistency, availability, and partition tolerance. Real systems make trade-offs based on their needs. Understanding how these trade-offs play out in practice is crucial for designing resilient systems. Sharding is a technique for splitting data across multiple databases or servers. This allows systems to scale horizontally, handling more data and users without overwhelming a single machine. Real-world sharding strategies must consider data distribution, balancing, and resharding as needs change. Microservices break large applications into smaller, independent services. Each service can be developed, deployed, and scaled separately. This approach increases flexibility and resilience, but also introduces new challenges in communication and coordination. In a microservices environment, services need to find and communicate with each other. Service discovery systems keep track of available services and their locations, enabling dynamic scaling and failover. Real-world implementations use tools like Console or etc. for this purpose. API gateways act as a single entry point for client requests in a microservices architecture. They handle routing, authentication, and rate limiting, simplifying the client's interaction with the system. Real-world gateways like Kong or NGINX are essential for managing complex service ecosystems. Message queues enable asynchronous communication between services. By decoupling producers and consumers, queues improve system resilience and scalability. Real-world systems use tools like RabbitMQ or Kafka to handle millions of messages per second. Distributed caching spreads cache data across multiple servers, reducing latency and improving performance. Systems like Redis or Memcached are widely used in production to handle large-scale caching needs, ensuring fast access to frequently used data. Content delivery networks, or CDNs, distribute static content like images and videos across servers worldwide. This reduces load times for users and offloads traffic from the main servers. Real-world CDNs like Cloudflare and Akamai are essential for global-scale applications. Database replication copies data across multiple servers to improve availability and fault tolerance. If one server fails, others can take over, ensuring continuous service. Real-world systems use replication to achieve high reliability and disaster recovery. Failover mechanisms automatically switch to backup systems when a primary system fails. This ensures high availability and minimizes downtime. Real-world implementations use health checks and automated scripts to detect failures and trigger failover. Monitoring systems track the health and performance of applications, while alerting systems notify engineers of issues. Tools like Prometheus and Grafana are widely used to visualize metrics and set up alerts, enabling rapid response to problems. Logging systems collect and store logs from applications and infrastructure. These logs are invaluable for debugging, auditing, and understanding system behavior. Real-world systems use centralized logging solutions like Elk Stack or Splunk for efficient log management. Authentication systems verify user identities and control access to resources. Real-world implementations use protocols like OAuth or OpenID Connect, balancing security with user convenience. These systems are critical for protecting sensitive data and maintaining trust. Authorization mechanisms determine what actions users are allowed to perform. Role-based access control, RBAC, is a common approach, assigning permissions based on user roles. Real-world systems must balance flexibility, security, and ease of management. Rate limiting protects systems from abuse by restricting the number of requests a user can make in a given time period. This prevents overload and ensures fair usage. Real-world systems implement rate limiting at the API gateway or service level. Circuit breakers prevent cascading failures by temporarily blocking requests to failing services. This allows systems to recover gracefully and maintain overall stability. Real-world implementations monitor error rates and automatically trip the breaker when thresholds are exceeded. Feature flags enable teams to turn features on or off without deploying new code. This allows for safer releases, A/B testing, and quick rollbacks. Real-world systems use feature flag platforms to manage experiments and control user experiences. Continuous integration, CI, automates the process of building and testing code with every change. This ensures that new code integrates smoothly and reduces the risk of bugs. Real-world CI systems like Jenkins or GitHub Actions are essential for modern development workflows. Continuous deployment, CD, takes CI a step further by automatically deploying code to production after passing tests. This enables rapid iteration and faster delivery of features. Real-world CD pipelines use automated testing, approval gates, and rollback mechanisms. Infrastructure as code, ISC, allows teams to define and manage infrastructure using code. Tools like Terraform or CloudFormation automate the provisioning and configuration of servers, networks, and databases. This approach increases consistency and reduces manual errors. Containerization packages applications and their dependencies into lightweight, portable containers. Tools like Docker make it easy to deploy and scale applications across different environments. Real-world systems use containers to improve consistency and resource utilization. Kubernetes automates the deployment, scaling, and management of containerized applications. It handles scheduling, health checks, and rolling updates, making it easier to run large-scale systems. Real-world companies rely on Kubernetes for reliable, scalable infrastructure. Service meshes manage communication between microservices, providing features like load balancing, encryption, and observability. Tools like Istio or Linked simplify complex networking tasks and improve system reliability. Real-world systems use service meshes to enhance security and monitoring. Autoscaling systems automatically adjust resources based on demand. This ensures that applications remain responsive during traffic spikes and save costs during low usage. Real-world autoscaling solutions monitor metrics and scale resources up or down as needed. Disaster recovery plans ensure that systems can recover from catastrophic failures. This involves regular backups, redundant infrastructure, and tested recovery procedures. Real-world companies invest heavily in disaster recovery to protect data and maintain service continuity. Data migration involves moving data between systems or formats, often during upgrades or cloud transitions. Real-world migrations require careful planning, validation, and rollback strategies to minimize downtime and prevent data loss. Blue-green deployments reduce risk by running two production environments, one live blue and one idle green. New versions are deployed to the idle environment, and traffic is switched over once validated. This approach enables quick rollbacks and safer releases. A/B testing allows teams to compare different versions of a feature or interface with real users. By measuring user behavior, teams can make data-driven decisions and optimize products. Real-world systems use A/B testing platforms to manage experiments and analyze results. Observability combines monitoring, logging, and tracing to provide a complete view of system health. This enables teams to detect, diagnose, and resolve issues quickly. Real-world observability platforms integrate multiple data sources for comprehensive insights. Security is a top priority in every real-world system. Best practices include encrypting data, regular vulnerability assessments, and strict access controls. Real-world systems implement layered security measures to protect against evolving threats. Studying these 18 real systems, you'll gain a practical understanding of the challenges and solutions that define modern software engineering. From URL shorteners to microservices, caching to disaster recovery, these systems cover 90% of what you'll encounter in production. Remember, the best way to learn is by exploring real products, analyzing their architecture, and applying these lessons to your own work. Keep building, keep learning, and you'll become a stronger engineer.